Everybody get your fucking hands up.
Before we start the discussion of erratic motion, let's again take a look at the three basic kinematic equations. These tell us that if the position s is the original function f of time t, then the velocity v is the first derivative function f prime, and acceleration a is the second derivative function f double prime. And we learned from calculus how to graph an original function as well as its derivative functions. So if you recall, for continuous motion, the position function consists of only one equation. For example, s equals to 15 times t minus 150. In this case, t, the time, is in the unit of second and s is in the unit of meter. Based on this equation, we can graph the relation between s and t. And this is the st graph. We can do the differentiation and find out that the velocity equals to ds over dt, which is a constant 15 meters per second. We can graph this constant function, and that's the vt graph, which shows the relation between velocity and time. And lastly, we can do differentiation again and get acceleration a equals to dv over dt, which is a constant 0. And we can graph this constant function as well and get the at graph, which shows how acceleration changes with time in general, but in this case, acceleration is 0 at any time. And let's quickly look at another example. Here we have another position function given as the function of time. And again, this is for a continuous rectilinear motion. And based on this function, we can sketch its graph, which is the st graph that tells us how the position changes with time. And if we do the differentiation, we get the velocity as a function of time. And we can sketch its graph as well, and that's the vt graph. And lastly, we can do the differentiation again and find that the acceleration is a constant 2, and we can graph this constant function and get the at graph, which shows how the acceleration relates to the time. And now for erratic motion. It simply means that the position-time dependence cannot be fully characterized by just one equation, but need to include more than one equations that apply to different time periods. In math, we know that a function like this is called a piecewise function. And chances are the velocity function and the acceleration function are piecewise functions as well. And we also learned in calculus how to graph piecewise function. Keep in mind that for erratic motion, all the three basic kinematic equations still apply. However, when you sketch the graphs for erratic motion, you want to be careful with where each time period begins and ends. Let me demonstrate with two examples. For the first example, we are given the piecewise function of acceleration as a function of time. We also know that the initial position and initial velocity are both 0. We are asked to construct the st position time graph, vt velocity time graph, and at acceleration time graph. The at graph is the easiest to sketch since the function is given here. So for the time period 0 to 10 seconds, we sketch the first equation that a equals to 0.4 times t, and that's a linear function. And we graph it up to the point that t equals to 10 seconds. Then for the second time period, from 10 seconds to 20 seconds, we sketch the second equation that a equals to a constant 2.4, and that's a horizontal line on our graph, again from 10 seconds to 20 seconds. And then for the last time period, 20 seconds to 30 seconds, we sketch the last equation that A equals to a constant 0. So on the graph, again, that's a horizontal line. If you wish to, you can connect the time periods with dashed lines, but just keep in mind that in math, the graph of the function does not include dashed lines. So that completes the AT graph. It shows us how the acceleration changes with time. Next, let's work on the VT graph. We need to use this kinematic equation because it provides the relation between acceleration and velocity. So for the first time period, because A equals to dv dt, therefore A times dt equals to dv, substitute in that A equals to 0.4 times t, and then we can integrate both sides and get velocity equals to 0.2 times t squared. Pay attention here to the integration lower limit. It is 0 because this is the given initial condition that initial velocity is 0. So on the VT graph, for the first time period from 0 to 10 seconds, we can sketch this equation V equals to 0.2 times t squared. And it is useful to calculate that at the end of this time period, the velocity has increased to 20 meters per second. Then we do the same thing for the second time period from 10 seconds to 20 seconds. Same integration, substitute in A equals to 2.4. Now, look at this lower integration limit for time. We are integrating from the beginning of this time period, which is time equals to 10 seconds. And here, we are again integrating from the velocity at the beginning of this time period, which is velocity equals to 20 meters per second. And after the integration, we get the velocity equals to 2.4 times t minus 4. And we sketch it on our graph. And also we calculate that at the end of this second time period, the velocity has become 40 meters per second. And similar thing for the third time period from 20 seconds to 30 seconds, same integration. Watch out for the integration limits, and then get the last equation, sketch it on our graph, and that completes our velocity time graph. So we can organize the velocity time function here as a piecewise function. And now we can use this to find the st function by applying this kinematic equation that relates the velocity to position. The procedure is very similar to the previous step. For the first time period, we do the integration, and we get position equals to 0.067 t to the third power. We sketch it and calculate that at the end of this time period, the position is 66.7 meters. Continue on for the second period. Watch out for the correct integration limits, and then sketch the function on our graph and calculate that at the end of the second period, the position has increased to 387 meters. And lastly, for the third period, same integration. Be careful with the integration limits again, and then get the last part of the st function and sketch it. And we can calculate that at the end of 30 seconds, the position has become 867 meters. And that completes the st graph. And the position as a function of time, as a piecewise function, is organized here. And here are the three motion graphs, the st graph, VT graph, and AT graph that we were asked to construct. And this completes this problem. I would advise you to study these graphs and see how these are the graphs for an original function and its first and second derivative functions. Now let's look at an example that is not so straightforward. We are given not a function of time, but this acceleration as a piecewise function of position. And also we are told that the initial position is 0 and the initial velocity is 10 meters per second. We need to construct the vs graph, the velocity as a function of position. But in addition, we need to answer the question that at what time the position reaches 600 meters. In other words, we also need to find the relation of position and time. So let's look at the first part. For that, we need to use this equation, ADS equals to VdV, since we have the AS relation and we need to find velocity. So for the first period, between position 0 and 200 meters, we substitute in the acceleration equation that A equals to 0.02 s and integrate both sides. Here, the initial velocity is 10 meters per second, and that is our integration limit here. We get the velocity equals to square root of 0.02 times s squared plus 100 after the integration. And this is velocity as a function of position, and we can sketch this first period on the VS graph. And we need to determine that at the end of this period, the velocity is 30 meters per second. And for the second part, position between 200 and 600 meters, we follow the same procedure. We sketch the second part on our VS graph, and we can calculate that when the position has reached 600 meters, the velocity is 50 meters per second. And this completes the VS graph. And the velocity function is organized here as a piecewise function. And again, this is a function of position. And let's move on to the second part of the problem. To determine at what time the object reaches the position of 600 meters, for that, we need to use this equation, v equals to ds dt, because we have the vs relation already, and we need to find time. So for the first period, we rearrange the kinematic equation and substitute in the velocity equation so we can integrate both sides again. You might need to use an integration table here for help, but this is what we get after integration. You can also use a numerical method or graphical method to do the integration. And now we can sketch the first part of the time position graph. And we can also calculate that at the end of this period, the time is 12.5 seconds. And we do the same thing for the second part. Integrate. Once again, make sure you have the correct integration limits. And then now we get the second TS equation. And from here, we can calculate that at S equals to 600 meters, T equals to 21.7 seconds. And that is actually the answer we're looking for. But we can still complete this graph. Notice that this is a TS graph, but we know that time is always an independent variable. Therefore, we might want to sketch the ST graph instead. All we need to do is to graph the inverse function for this one. And we can get the ST graph that shows how position changes with time. This graph is not asked for, but it is very informative. And now please answer the following questions.